So I'll be talking to you about solving the plasma kinetic equation numerically on smooth manifolds with continuum methods. I'll start with some background and just a quick high-level overview of this problem. In the past decade or so, people have used general relativistic particle and cell to simulate the full kinetic systems of jet launching and magnetized disks around compact objects. But ultimately, where the general relativistic particle and cell representation of a plasma breaks down or has difficulty is when you have strong density gradients or you need detailed phase space information. In which case, a kinetic continuum scheme, shown to the right, is a possible alternative. Here, you resolve your full phase space on a grid. I'm showing a pulsar gap discharge problem here, where you both are able to self-consistently solve the atmosphere and the magnetosphere of this problem, even though there's an extreme density gradient between the two. The main limitations of the kinetic continuum solve has been their development, and they have not yet been extended to general relativistic configurations, and that's the goal of my thesis: how to take the special relativistic solver and extend it using the lessons from gyrokinetics and tetrads approaches to form a general relativistic kinetic continuum approach. I'm going to start my talk by discussing the outline of this approach, which is called a canonical Poisson bracket. It's going to be used to solve the kinetic equations. I'm going to start in the non-relativistic limit and then explain how to extend this after doing some benchmarking to general relativity. Ultimately talk about the limitations of using canonical coordinates and how these can be overcome by using a non-canonical tetrads bracket. All right, so part one, the canonical Poisson bracket approach. So I want to start with the differences for an example problem of Kavli-Helmholtz instability on the surface of a sphere. Here you have a configuration space and you want to solve it potentially with fluid dynamics. This is going to be a 2D plus time problem where you evolve the hydrodynamics equations, moments, densities, velocity, and temperature, and so on. And ultimately you truncate this with closure. And on the right, the kinetic continuum approach. This is now a 4D problem. You have both your configuration space and your velocity space at every single point. This is now 4D plus time. It's going to be solved with the Vlasov equation for this example. And it's going to involve your phase space quantities such as your positional variables, your momentum variables, and time. But no moment closure will be required at this point since you have your full velocity space information. To talk about quickly the generality of the solver, we want to be able to handle not just this case, but any sort of smooth manifold. So this could include the surface of a sphere here, but it could also be things like annular disks, toroidal coordinates, or space-time with gravity. The core of the canonical Poisson bracket formulation is a representation of the Hamiltonian. Here we just have a non-relativistic free-streaming Hamiltonian for h is p squared. Your h is going to be represented in terms of upstairs positions and downstairs momentum coordinates, your canonical pair. So your bracket associated with this evolution is going to be in a canonical form, the canonical Poisson bracket. And the Liouville's theorem is going to be the time derivative of your distribution function f plus the bracket for your advective terms. This is ultimately the core of our solver. It just requires these simple equations. And gets implied geodesic motion from this. You can calculate this by computing gradients of your Hamiltonian and verifying that it matches the equation of geodesic motion. But we didn't need any explicit appearance of our Christoffel symbols. What we're going to discretize is our Hamiltonian h and our distribution function f. How we go about discretizing this, we're going to rewrite our Vlasov equation in a conservative form. We've rewritten the bracket here as a divergence over our phase space. And because we're in canonical coordinates, this takes a particularly simple form without any factors of Jacobians. It has an associated semi-discrete weak form by integrating against the test function w and integrating over our conservative form of our Boltzmann equation. We end up with this form of our Vlasov equation that's amenable to either proofs of our system, our discrete system, or our ability to come up with update equations using different representations of your spatial grid. So the way that we're going to go about discretizing this, we're going to represent our distribution function f of h in terms of polynomial expansion on each phase space cell. So these bases vi are orthonormal, and then we are evolving the coefficients f of I in time. The core of this is the discontinuous Galerkin scheme. Within each cell, our solutions can be represented as a sum of polynomials. These are going to be coefficients times the polynomials that construct f. F is going to be allowed to be discontinuous between cells, so our problem is ultimately a local one for update equations for f. But since we have Hamiltonian, it's going to be describing our equations of motion for both non-relativity and relativity. It's going to be static, and we're going to restrict it to the continuous subspace. The reason that we want to restrict this to the continuous subspace is that we want a phase-space incompressibility condition ultimately for our proofs of conservation laws and stability properties. So this continuity in the Hamiltonian is going to be it's what's going to enable us to write a characteristic velocity lemma that's associated with this. So the components of the characteristic velocity alpha h or normal to a phase-space cell is going to be continuous. The proof of this comes from the anti-symmetry property of the Poisson tensor. This applies to both canonical and non-canonical brackets. And essentially it states if you want to calculate a characteristic that's normal to a surface, any of the gradients that you need to take are going to be tangent to the surface, in which case, since your Hamiltonian is continuous, your characteristics normal to the surface are also continuous. This is overall a proof of phase-space incompressibility in a different form, but it allows us to then write discrete discrete properties of our scheme. For instance, the total number of particles is going to be conserved exactly. The spatial scheme will further conserve energy exactly. This comes from our past proposition, as well as combining it with our discrete weak form. We can then show that for stability, we either conserve L2 norm or we monotonically decay the L2 norm of our system. Ultimately, we're going to choose an upwind scheme because this slight L2 norm decay overall enhances stability and dissipates any high frequency noise that we might get. The differences here is going to be dependent on the states of the left and right hand of a cell interface. So ultimately, when you're using a high order scheme like DG, the differences between your left and right states between cells is very small. So this is only a small amount of numerical dissipation that's being introduced to the system overall. Farther, as long as the discrete distribution f of h remains positive definite, we're able to say that the entropy is going to grow monotonically. The final bit that I want to talk about is going to be collisions and moments of our distribution. We can define the non-relativistic limit, density, velocity, and temperature. We're calculating the integrals in terms of the downstairs components of momentum, P1, P2, P3, where the fact you've expanded in terms of these dual bases for positions and tangent bases for your momentum is going to give you a volume factor at every point from your tangent space, so this factor JC. That's why it's going to appear in our definitions of density, velocity, and temperature. Well, we can ultimately use these to come up with a local equilibrium that's moment matched. This is going to be our FEQ, and that can be used for things such as a BGK collision operator on the right-hand side of our Vlasov equation. It's going to be, since it's moment matched, conservative in momentum, velocity, and density, and not change any of these properties. As well, it's written in such a way that it's implicit. We have no time step restriction, and certain parts of our domain can be fluid-like, while other parts of the domain are purely free-streaming kinetics. This will also be used in things like calculating transport coefficients. The benchmarks of this are particularly well suited in this highly collisional limit. The top row is going to be the integrated moments of our kinetic distribution and the final time step of an annular disk sod shock problem. The bottom row is going to compare the results, the moments of the kinetic distribution, to that of an Euler solve, and ultimately we get excellent agreement. We can verify things at this point, such as checking that we do indeed have total density and total energy conservation of our overall discrete system. The example I teased in the beginning is Kelvin-Helmholtz instability on the surface of a sphere. Here you set up initially counterpropagating blobs that are in your computational coordinates of theta and phi. This is going to map ultimately to your physical coordinates, your physical domain, where we're going to evolve the density in time. This is going to be the movie of that, where I now include some more moments. These are going to be your velocities and your temperatures, where you've initialized some random noise in order to excite the Kelvin-Helmholtz mode. Evolving this in time, you can see the classic formation of the cat's eyes. They'll eventually merge together and saturate towards that of the system. It's important to note this is a full 4D kinetic continuum simulation, so we do have at every point your local velocity space information. So it serves both as a test of our system in the fluid-like limit, but also we can get detailed phase space information out of our system. This is really where kinetic continuum methods shine. You can grab your local distribution function in configuration space at a certain number of points, and we're going to plot these to the right. Here we can see that the differences are going to be 10 to the minus 5 and 10 to the minus 6 when calculating the difference between F and a locally equivalent FEQ in order to calculate things like transport coefficients and new closures for your system. So just an overview of this bracket solver. The CAMPB bracket works in any dimensionality from 1x1v to 3x3v. It can handle flexible geometries, and it only requires changing the metric function, which is essentially baked into a single scalar field, the Hamiltonian. This is multi-GPU parallel, and we can handle things such as 6D phase spaces, and it has excellent scaling of the isolated CAMPB solver. How do we then go from this non-relativistic system to the general relativistic system? The first thing we'll have to derive is a Eulerian observer for Hamiltonian, written in terms of the gauge variables alpha and beta, and our particle variable, or sorry, our gauge variables alpha and beta, and our particle variables gamma and p. We can express our Hamiltonian in the same pair of canonical coordinates, our upstairs positions and downstairs momentum, as we did before, and recycle the entire machinery that we had for our canonical bracket solver. So these characteristics can then be verified to match those of the geodesic equation. So we're still evolving what we think we're evolving, which is the geodesic motion of single particles. And for plasma advection and other things like collisions, you can add these onto the right-hand side of the Vlasov equation at the bottom. So as a test case for qualitatively verifying our motion, we can check the collisionless motion around a Schwarzschild black hole, where we have particle precession of a blob. Since we're in kinetic continuum, doing a delta function in single particle motion is rather difficult. So what we do instead is initialize a blob in phase space and qualitatively at this point compare the evolution, because we've already verified that the geodesic motion is what ultimately we're simulating, and that here our final states between our precession agree at this point qualitatively. So the ultimate limits of using the canonical Poisson bracket formalism and canonical coordinates is actually an inefficient use of the phase space. So this is going to be an example of an annular Sod-Shock case where you want to set up initial conditions on a uniform grid. So we're going between a radius of 0.5 and 1.5, and we want to project equal density and equal temperature distributions. But in canonical coordinates, you're going to pick up a factor of your radius because of an unnormalized component in your dual vector here. So p theta is going to carry a factor r, so on the same grid, you're going to have two different resolutions. When you have extreme amounts of curvature and more general cases like helical or toroidal coordinates or GR with gravity, this can become a pretty extreme difficulty. You have to be able to resolve this or have some sort of non-uniform grid. But the way that we're going to approach normalizing our grids, in this case and in general cases, is going to be with a tetrad formulation. This is going to then employ a non-canonical bracket for evolving our systems. So what are the tetrads that we're going to use? First, we were already working with frame vectors. These dot together to give you your curved space, or your ADM metric. And we're going to define via relations of Verbian fields a local tetrad frame, which is orthonormal. This is essentially going from a problem to the right in a 3D spatial hypersurface, your unnormalized volume JC from the relative tangent vectors to your now normalized volume in your triads in terms of these sigmas. So where did this approach originate from? This came from GR fluid and EM modeling, where in standard approaches you have a rapidly rotating walled solution. You want to calculate the Riemann problem to update the variables between cells. In the classic case, where you use the Riemann problem using these GR variables, it can be very difficult in rapidly rotating cases to not introduce numeric noise through calculating the Riemann solve. But for a local orthonormal tetrad frame, or tetrad's first approach, derived by Jonathan Gerard, Amar Hakim, Jimmy Juno, Jason Temparge, and others, you're able to transform your local GR variables into a flat space and solve the special relativistic problem there, alleviating this difficulty on your GR solvers. And this is, double precision that you're still introducing numerical oscillations and stuff. So this is able to then stabilize that approach. What we're going to do for solving the tetrad bracket is actually going to be quite different. So we're going to start with our phase space Lagrangian. This is written out in a vectorized form in terms of our positions and our momentums here. We can re-express our variables of the phase-space Lagrangian, still using the same positional expansion, but now our momentum expansion is going to be written in terms of our orthonormal triad basis, so the projected tetrads. The phase-space Lagrangian, when you plug in these different representations, is going to be written in terms of components here. We can take the variations of this phase-space Lagrangian and ultimately come up with our Euler-Lagrange equations. These are from the Euler-Lagrange equations. We get our equations of motion. From these, we're able to construct a tetrads bracket that's non-canonical that ultimately describes our phase-space evolution with this local special relativistic frame describing the momentum. So this takes on a similar form. We just add an NC for non-canonical here to our Vlasov equation. But the real magic of this system is that you have this tetrads representation of your momentum. You can do things such as collisions at single points, as well as coupling to the tetrads first representation of your Maxwell's equations. Amongst other things, that gives you a lot of flexibility in how you design your scheme. But also, we can use this for calculating equilibrium and verifying that our equilibrium now is going to be correctly distributed. We don't have this inefficient use of our phase-space grid like we had in the canonical coordinates to the top. So I've now exacerbated the annular disk case where you have points, your red point at a radius of 0.5 and a blue point at a radius of 10. You had this apparent phase-space compression effect where you would need extreme amounts of resolution in your p theta direction in order to resolve this specific case. Whereas in the tetrads bracket, you now no longer require extreme momentum grid resolution, and you no longer require a larger domain. So you can be able to solve this at a single point on a uniform grid across any part of your spatial domain. So the way that you can see this is cleaned it up is for annular disk, you can see before we had this normalized coefficient 1 over r, but that's now disappeared with our orthonormal tetrads representation. This is not just for this one case. I want to emphasize it applies to every single case that you could potentially have. This includes things like toroidal coordinates or any sort of extremely sheared grids that you might get. In summary, we've developed a new formulation for solving the kinetic equation on curved spaces using this canonical Plon bracket formulation. I've showed that it can be applied to both non-relativistic and relativistic limits, and that has provable properties such as density conservation, momentum, or energy conservation, and L2 stability properties. I've benchmarked the solver to a number of cases and identified limitations in overall using canonical coordinates. And my current work of my PhD thesis, I've talked about the neutral advective component of this, was coupling in Lorentz force terms and a DG representation of the GR Maxwell's equations, and then finally adding on BGK collisions. So by the end of my thesis, I hope we'll have a full Maxwell-Vlasov BGK system with DG kinetics and arbitrary dimensions. So thank you very much for your attention. Open up to any questions.
So we have Alex right there.
Oh, thank you for the nice talk. This is really interesting. Do you do anything to ensure that f is always larger than 0, or in practice it doesn't matter?
This is a great question. So to keep positivity of f, we do not guarantee the positivity of f is a short answer. You would need to do a polynomial order 1 expansion at most in order to guarantee that your distribution function remains positive, in which case it is provable that you could come up with reconstructive methods that maintain the positivity. In these cases, they do not guarantee that property, and we, based on the initial conditions, essentially you have to verify that you haven't violated this significantly during your simulation. Well, thank you for your question.
Yes. Oh, yeah. Right there.
Thanks for the talk. I'm a big fan of computational developments at all levels. So, but unfortunately, this also begs the question: how does it compare to current approaches? You know, if you were to sell it to me, for example, you know, we just got a talk about entity which can do these kind of simulations very efficiently. How would you rate the efficiency of this approach versus traditional PIC, for example, that we know sort of works at this point in time pretty well for what is needed, and what is then the perspective to scale this up maybe to, I think I saw some scaling plots maybe that you were showing, but I couldn't really read it. So maybe if you can recap that, it would be great.
Sure. I'm actually going to go to, why did we choose these methods slide? So essentially comparing between PIC and Continuum. Continuum will be more expensive, but what actually makes Continuum tractable and has been a recent development, and not a lot of work has really been done to compare the computational efficiency of the two with state-of-the-art for DG kinetic continuum. So primarily it is the DG algorithm that enables us to go up to 60 phase spaces, for instance. And it's because of a combination of things. First, a higher order representation allows us to use very coarse grids. Our momentum grids, for instance, can get away typically on the simulations I showed with between 8 and 12 cells per momentum space dimension. Rather than if you're using like a first order method, this might take hundreds of cells per dimension. It has good parallelization properties, so you can end up in like, at least if you have extreme density gradients or something for particle and cell, this is a place that the DG like kinetic continuum scheme will shine. It's also if you are doing a problem or you want to do a problem that has or requires extreme detailed phase space information on large scales, that's something that it enables. So it will probably always be more expensive than particle and cell, but it's the physics and things that you can look at that are different really between the two, the problems that you can answer with it.
More questions? Well, I have actually one question that is kind of two. So we've heard a lot about including extra physics like radiation reaction, QED processes and all that. We have also seen people that are doing this, right? So changing, rewriting Vaso equation, including these terms. So how do you see that those techniques integrated in your framework?
I see them building on top of it. For at least the scope of my thesis, this is for me, it's going to take probably another year or two of development to complete. But we also have terms in the code that this is all written in Jekyll that can handle radiation that will be able to fold in seamless, especially with this local tetrads frame where we can describe our special relativistic equations using, or like anything coupled to GR can be described at a point with our special relativistic equations.
Could you outline how difficult it would be to add the red and blue terms in GR? Or, I mean, is it a simple thing, or you have to do some major development?
It's somewhere in between. So the current way that we're intending to add this to our code is to add on to our characteristics at the end of each time step the contributions of Lorentz force terms to your momentum space push. So this already exists for the special relativistic case. Essentially, for the GR case, we would need to add on essentially rewrite our solver to be compatible with the alpha beta that will be introduced from our gravity. For the BGK collision operators, we already have, this is the first paper on here that we just recently published at JPP, talks about how to do the algorithm for collisions in a DG sense using a BGK operator in a special relativistic frame. And since we have the tetrads, we're able to immediately apply and recycle this entire algorithm for BGK collisions.
And what about the field solver that you use for D and B?
So the field solvers currently, and we have two different solvers in Jekyll. One is going to be for special relativistic flat space, and the other is going to be a finite, that's DG. The second is going to be a finite volume solver that is for GR. That's probably going to be the most major component of this red term here, is going to be extending the Maxwell equation solver from the special relativity to DG, but we intend to recycle the exact algorithm for Tetrad's approach to the Maxwell equations.
But as a follow-up, do you aim to have the full care GR solver, or are you going to work in kind of other approximations?
That is ultimately one of the goals outside the scope of sort of the immediate work that we're doing, is we'd like to have a self-consistent GR evolution.
Okay. Any other questions? Okay, so if not, let's thank Grant again. Thank you very much. Thank you.